All right, so recording is rolling. Welcome to Tuesday, January 11th. So today we're gonna wrap up this pendulum lab from yesterday. We finished about 90% of it yesterday. We just had to wrap up a couple of things. Actually, that might be pretty good how that played out because you guys get to see us one more time, think about it. Last graph, formula, okay. And then I'm gonna go to give you guys a few notes today and do some demos, and then that'll be as far as we can get today. So yesterday, you were trying to figure out what formula is going to govern the motion of a pendulum. And we were thinking about these different variables, like, well, there's maybe some mass of a bob, there's some angles maybe it can swing from the vertical, there's some length of the pendulum, and there's some amount of time it takes to swing back and forth. We were also considering that this is in a gravitational field, which does end up being important, but we're stuck in one constant gravity field, so kind of hard to test for that. And the way we approach this lab was to relate everything to time period. So changing mass, how does that affect time period? Changing starting angle, how does that affect time period? Changing length of the pendulum, how does that affect time period? And I have you guys' paper right here. Pull this up. That's it. As you could keep the other two controlled. So for example, changing length, how does that affect time period? We're using constant mass and constant angle, the whole deal. Okay. But what we got from that, well, here's your guys' data. Here's 3 data tables because 3 separate experiments. Okay. We made the graphs. Time as a function of mass ended up being no relationship. So as you make the mass bigger, 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 time period didn't care. This does whatever it's doing based on the other features of the pendulum, like its length. Okay. If you change the starting angle, same story. Okay. So for like 10 degrees, 20 degrees, 30 degrees, didn't matter. It was just the same time period over and over. So also no relationship. The only variable out of those that we tested that there was some kind of relationship was length. If you made the pendulum longer, it did take more time to swing back and forth, but kind of an interesting way, because it's not a direct relationship. Let's say if you double the length, you do not necessarily double the time. Okay. Looking at this curve that actually looks more like a square root type relationship. And I wanted to remind you guys of this axis manipulation trick that you guys have seen in past labs, and also AP likes this a lot. So this, what I'm about to show you guys, how we're going to finish the lab, is totally something that could pop up on the AP exam. Okay? So let me go back to some pretty fundamental algebra, just very fundamentally, just y equals the square root of x. Okay? So y equals the square root of x might have this data table, like the square root of 25 is 5, for example. Plot those points on a graph. Hey, it makes that classic hook shape. It looks a lot like this time period versus square root, or sorry, time period versus length graph, right? So we're already starting to suspect that it's probably square root, but we want to check for sure. Like, how do you know it's not the cube root or some other type of graph? Right? Well, if it really is a square root, then you can do this axis manipulation trick that we've also done before in this class on different labs. So if you graph not y versus x, but y versus the square root of x, if it was truly exactly a square root relationship, then all your points would line up exactly like this. You can try this with this table of numbers, and it turns out to be true. Alternatively, you can square both sides of the equation and do y squared versus x, and those points would also line up. Well, the graph would look a little different, but it still line up. Okay? All right, so let's try that on this graph to finish this lab. Now, I did give you guys 2 graphs here because there's 2 different ways you can finish this lab off. One way is you could graph time versus the square root of length. The other way is you could graph time squared versus length. You could do either one of those. Did you? Yeah. Now, if this hook-looking graph here really is a square root, then either of these should line up into a straight line. We're just going to do one of them. I'm going to pick this top one, time versus the square root of length. Now, since you guys are AP, how you might see this possibly is this could be in one of your FRQs. You could have like some raw data that looks a lot like, say, this table, and then maybe like different students are trying to figure out how to figure out this relationship, and you being an AP student, you would know the equations, like you would know ultimately what's going to be the answer to this lab. It happens to be printed on this page. I'll point it out to you after we get to it. Okay, so you would know exactly how to manipulate the axis to do this. And here, you could do either of these. Okay, so we're going to do this one, time versus the square root of length. Let's see. This is, that was this table here. I'll let you guys a blank column. And AP likes to do this too. Sometimes they'll give you a table that has like either a blank column or a blank row, and then you can create your own variables. So we're going to go with the square root of the length. That's in the unit for that. It's going to be square root of some number of centimeters. Now it's a really weird abstract unit because this is an abstract idea, but should work first. So what is the square root of 79 centimeters? That's 8.89. What's the square root of 63 centimeters? That's 7.94. Square root of 57 is 7.55. Square root of 48 is 6.93. Square root of 38 is 6.16. Square root of 20 is 4.47. Okay. So you took all the length values, square rooted each one, let's get square root of length. All right, now we're going to graph time period as a function of not length, but the square root of the length. And hopefully this is a direct relationship, but we're going to find out. We're going to treat these like Cartesian coordinates, like x, y, x, y, x, y, all the way down. So see, the biggest square root length was 8.89. The biggest time was 1.75. So maybe I'll scale these axes up to like 10 and up to 2, maybe something like that. So square root length, this would be some square root centimeters versus time is still going to be in seconds. So you start at 0. Graphs always start at 0, 0. Right? Scale this up to 10. So 5, 10. Okay, so that should contain all that data. Then the time, well, I need to go up to 2 seconds. So call it 1 second, 2 seconds. Okay, so all my data should fit right in here. Looking for a linear relationship, we're about to find out if that's true. So the first coordinate is 8.89 over and 1.75 up. Okay. So 8.89 over 1.75 up. It's right about there. You guys are following along with me? 7.94 over 1.58 up. 7.94 over 1.58 up. 7.55, 1.50. 7.55, 1.50. Right there. 6.93, 1.37. 6.93, 1.37. 6.16, 1.21. 6.16, 1.21. Okay. And finally, 4.47, 0.87. 4.47.87. Right about there. Okay. Oh, look at those points. They really do line up on a straight line, don't they? And look at that. You can extrapolate backwards, and so that is a direct relationship. It goes through the origin, doesn't it? Right? Direct relationship, goes through the origin, has zero intercept. Yeah, so we did confirm what look like a square root curve, yeah, it does end up being exactly a square root curve. Right? T versus square root L is a direct relationship. So that's going to bring us to this box here. Well, here's the one I skipped. T squared versus L that would also line up in a straight line, give you the same information. So this says time period is proportional to. I used to write proportion that way. Now I tend to write it this way. Time period is proportional to. Okay? And the answer is square root of the length. That's what we got from this data. Proportional to is kind of like an equation, but it's saying it's part of a bigger equation. It's not the full equation. It's a partial equation. Right? It's part of a bigger one. Okay. So, hey, how about this? Let's see if you guys are following. What if I had a pendulum that was some length and I quadrupled the length of the pendulum, made it 4 times as long? What would happen to the time period? Get twice as much, right? It'd take twice as much time to cycle back and forth. Right? What if I made the pendulum 9 times as long? What would happen to the time period? Yeah, 3 times as much time, right? That's it, the square root relationship. Let me give you guys the full textbook answer. Time period is equal to, you can make this a full equation if you throw in some other parts. Like I remember gravity field was missing. Remember we were thinking, well, if you take this to the moon, which has really weak gravity, it would take a long time to cycle back and forth. So that sounds like maybe some kind of inverse relationship going on between gravity field and time period. Here's the full equation. Time period is equal to 2 pi times the square root of L divided by G. Ah, I see. There is some kind of inverse looking relationship between time period and gravity. So that makes sense. Right? And okay, and I see how this proportion, which is the answer to the lab, is yeah, that is a partial equation for the full textbook answer. Right? And here's where it is on AP's equations. It's right here. Time period of a pendulum equals, oh, look at that, 2 pi times square root L over G. L is the length pendulum, G is gravity field. Okay. So if you knew between length, gravity field, and time period, if you knew any 2 of those, you could solve for the third. Okay, that's just algebra. Okay. But then, of course, what AP wants you to know is the further stuff like proportions. But you guys just navigated that, no problem. You said, well, if it's 9 times as long, it's going to take 3 times to cycle back and forth. Okay. Look at the equation right above it. Time period equals 2 pi times square root M over K. See how that has the exact same structure, but it refers to something a little bit different, although it's also oscillation. This is if you have a mass on a spring, some spring constant K. You guys remember spring constant K? How stiff is the spring? Okay. So let's say there's a mass bobbing up and down and bobbing back and forth. I have an animation I'll show you guys in a few minutes. That's this, right? So how much time will it take to cycle back and forth? Well, if you know the mass of the block, you know the spring constant, pop, pop. There you go. Just like for a pendulum. I have these 2 posters hanging on my ceiling right here. So here's your guys' lab for the pendulum, and then right next to it is, you have a picture of the block on the spring. Okay. See what's coming there? Okay. So that's that. All right, next thing, you guys good so far? Let's do this. You guys got all the graphs, you guys got this answer at the end. Pass up your labs. I'll take this up from you guys so that you can get this off your desk. And then I'll give you guys a few notes here and we'll do a few demos and then I'll just have the lab so you don't have to worry about the great trick. All right, so pick this up from you guys. Thank you, everybody. All right, so give you guys some notes that involve both periodic motion and also wave motion. I'll tell you guys just for AP, let me tell you sort of how AP is structured and a little bit of history so you know some context what's going on. Unit 6 in AP's book is periodic motion, simple harmonic motion, like pendulums and stuff. There used to be tested a unit 10, which was waves and wave motion. Now, I've always taught these subjects together because there's a lot of similarities. They both have some time period and frequency and oscillation, blah, blah. So you guys are going to learn a bit about waves, so that'll be right. But anything that's waves is technically not being tested anymore on the AP exams, but you guys get to learn it, but it's not really being tested on, right? So let's look at this pendulum. Okay, so I still got this up here. So swing back and forth. And let's say I'm interested in the horizontal position of this bob as it's going back and forth, the horizontal position as a function of time. So time's ticking along, tick, 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 right? And I'm watching this bob. And it could go through this the center line, maybe I'll call that like 0, like as a reference point. It goes in positive territory, then back to 0, then negative territory, then 0, positive, 0, negative 0, and it just oscillates like that, right? And what if I made a graph? And I was wondering, I wonder what that graph is going to look like. We've got some paper. Actually, I'm going to make 4 graphs. I'm going to go with a portrait with this. So we've got landscape, portrait, going portrait. In case trying to follow on your notes, I want to do something really similar to what I'm doing. You guys remember back in kinematic motion, like dropping balls off cliffs? We were doing those like 3 graphs over and over. So this is going to be a really similar idea to that, except I'm going to make 4 graphs stacked on top of each other. And you'll see why by the time I finish these graphs. So we got 4 graphs set up. So now it's on like sideways T looking shapes. Okay. And the first one I'm going to call position as a function of time. Okay. So the position might be in some number of centimeters, and time could be some number of seconds, tick, 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 ticking along. Like for this bob, I'm interested in like how far to the right or the left is it from this this vertical reference line. Okay. And I could start keeping track of its position, whatever I want to. For simplicity, I'm going to start counting when it's crossing through this this line, this center line. Okay. So swing, 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 and boom, start right here. Okay. So it goes positive and then back to 0 and then to negative. Okay. What's that going to look like? Well, it's going to do something like this. So at time 0, I started at position 0. Okay. It was already in motion. Okay. It's going to swing into positive territory and then go back to the center line and then go into negative territory and then back to the center line and then back to positive, center, negative, center. It'll just like oscillate like this over and over forever, right? If there's no frictional losses, it could do that forever. Okay, just back, forth, back, forth, back, forth. Sure. Okay. Now this is like a classic wave type shape. Okay. Actually, this is a certain category graph that I don't know if we've ever talked about before. We've talked about no relationship, like either a horizontal or vertical line between 2 variables on a graph. We've talked about direct relationship, linear relationships. We've talked about inverse relationships. We've talked about power and root relationships. But this is none of the above. What kind of curve? What category of curve is this called?
Sine.
It is a sine curve. Yeah, this is a sine curve. And sinusoidal. And if you break down the word sinusoidal, oh look, it has sine in it. Right? Sinusoidal, like bouncing back and forth, oscillating, right? Just like a sine curve. Right? This has some properties. I'm going to blow this picture up on another page so you can see this better. But one of the properties is called amplitude. That's like from this center nodal line up to this crest right here. It's called amplitude. Okay. It has some other properties I'm going to point out. But what about if I want to make a formula? What is the position of that bob as a function of time? So position as a function of time. Okay. Well, in general, it goes like this. The amplitude multiplied by sine, you guys right, it is sine, that's why I started from the middle, okay, of 2 pi times the frequency, which I'm about to give you guys some notes to say what that means, okay, all multiplied by the time ticking along. Okay. Now that's kind of a general formula, and that's actually further than I really want to go with this class, but if you're really into waves and want to know about this, then that'd be a starting point. You could start to do some research on that. Okay. But I want to give you guys a simplified version of that. Sorry, point out a couple other things. Okay. So this A amplitude, you can like stretch the wave vertically. The frequency has to do with like its horizontal compression. So if you have a high frequency, it like smashes the wave in, makes it like high frequency. Okay. What if the frequency was 1 over 2 pi, so that this all just canceled out, and the amplitude was 1? Wouldn't you have something like this? like the position of the bob would just very simply be sine of t, right? That could be what that graph is, if I give an amplitude of 1 and say like a period of like 2 pi or something like that, right? So could just be position is sine of t. Right? Well, this is maybe a kinematic question, like what's its location as a function of time? And I know there are some other kinematic properties too, like how fast is that bob moving? Do you guys think that bob is moving the fastest right down at the bottom? Goes fast, slow, 0, slow, fast, speed up, slow down, speed up, slow down, speed up, slow down, speed, right? Do that? Okay. That's gonna bring me to, that's why I got these other graphs. So I can start doing V versus T. There's gonna be an A versus T. And I do have a fourth one, I'll save that one for later. So velocity might be like centimeters per second. Acceleration could be like centimeters per second squared, like that. And what do these graphs gonna look like? Well, we're just saying that when it's crossing through the middle, that vertical line, that it's going as fast as it's ever gonna go. So maybe I'll do it like this, like at time 0, it's moving really fast. That could be that point, right? I want to make some reference signs so I can line up these curves, because these curves are all going to be related to each other. They're all sinusoidal. So what parts are going to correspond to what parts? Right? I remember the crest of this x versus t represents as far out as it goes, but the velocity at that point would be 0, because that would be like this point right here. It gets as far out to the right as it's going to go, and its speed goes to 0. So that corresponds to this point on the v versus t graph, doesn't it? Okay. Then it swings back the other way, goes through the center again, moving really fast, just in the negative direction. That's kind of like this point on the graph. Okay. And you start to make all these points, okay, and say, okay, it starts to take the same shape as the original, just like shifted. You guys see that? Connect all the dots, it's going to go like this. Okay. And what is the equation of that graph? I bet a lot of you guys know. Cosine. Yeah, the velocity as a function of time is cosine of however much time has passed. Okay. Again, if you want to make it more fancy and manipulate it with the 2 pi f and the a, then that could also carry over too. Okay. I bet you especially knew that if you are in calculus, because you guys know that just like velocity is a rate change of position, cosine is the rate change of sine, right? Rate change of sine is cosine. Right? Okay, let's go down to acceleration. Right? Well, now we've got this rate change model framework. Right? If the rate change of sine is cosine, what is the rate change of cosine?
Negative sign.
It is negative sine. Yeah, exactly. So it's the same as the first graph, but upside down. So it's going to go kind of like this. So, okay, so it's always changing its acceleration also. And acceleration as a function of time is negative sine of however much time has passed. Okay. Huh. Okay, that's going to bring us to this fourth graph, which is the next rate change. Now this, I think I may have mentioned like once or twice ever before. We almost never talk about it. Does anybody happen to know or remember what is the rate change of acceleration?
Is it jerk?
Jerk. Yeah. Okay. You guys remember this. Jerk. Yeah. So jerk. Right? And that might have units of, for example, centimeters per second cubed. Right? It's like a rate change of acceleration. Right? Okay. Well, you guys see a pattern developing, right? So rate change of sine is cosine. Rate change of cosine is negative sine. What do you guys think the rate change of negative sine is?
Negative cosine.
Negative cosine. And that's gonna do, let's see, something kind of like this. So jerk as a function of time is negative cosine of however much time has passed. That. And the reason I wanted to bring in jerk is because that actually completes a 4-part cycle. Because if you take the rate change of negative cosine, guess what you get back to? Positive sine, and then we just cycle through again, right? So that's all 4 parts of this cycle. Like, you guys see that? You just like keep going over. If there's no frictional losses and you have a perfect ideal pendulum, then just keep taking rate change forever. Let's do this. I'm going to take any one of these curves. Let's say like the sine curve. I'm going to blow this up, and we're going to look at different properties of Okay, you guys got all this? Okay. Okay. Gonna blow up one of these curves so we can look at properties of waves. Okay? Let me get a horizontal central node line going. There's maybe something like that going on. Okay. Oh, what are some different properties of this wave? Well, one property that was starting to talk about a little bit was amplitude. So that's A, amplitude. Okay. That's from the center node line to say like the crest. Oh, you might call that a crest. Call this a crest. Call this a trough. If you're talking about standing waves, sometimes you refer to this as antinodes, and then these points where it crosses the center line would be called nodes. I've got some animations for you guys too, where you have to see this also. So, how about this? I wonder what is the shortest, like the most fundamental segment you could take and copy paste it next to itself, and it would make a full continuous wave. Like if, say I do this, say I look at like that hill right there, and I copy paste that next to itself, wouldn't it be like hill, hill, hill? Okay, well, that wouldn't be a full wave because we wouldn't have the bottom part. Okay. But how about this? How about this? What if you go from one crest to the adjacent crest, from crest to crest? Like this distance right here. Okay. You see how you could clip that out right there and copy paste it next to itself, and it would, that would be like a full process, wouldn't it? Right, crest to crest. Okay. That distance, crest to crest, is called one wavelength. That's represented with Greek letter lambda, one wavelength. Okay. Now, you don't have to measure crest to crest. You can measure trough to trough. You guys see that would be the same distance. Right? That's 3 meters. That's 3 meters. Same thing. Okay. Or how I like to do it a lot is to go from one of these nodes, skip a node, and go to the next node. Okay. So that would be like one full S shape. Sometimes I call it that, like one full S shape. Kind of a Griffin colloquialism, but that's also one wavelength. Yeah, that S shape right there could be like a fundamental length. You could copy paste it next to itself. Right? It's a different way to measure the same length. Right? That could also be like 3 meters, same thing. Right, some other properties of, I'll go ahead and label this node. Should be true for like a standing wave. If you see something like that. Other properties of this. Let's say you're sitting on the dock at the ocean, and you're watching these waves come in, and you're watching the water go like bob up, down, up, as it's like crossing some point. It's like hitting against the dock, right? Bobbing up, down, up, down, up, down. Okay? And you maybe you could measure what the distance is between wave crests. So you could do that. You could start to make like physical sense of this. Maybe you brought a stopwatch with you and you're timing. Right? You said, oh, it takes like so many seconds to go from crest to crest, like bob, bob. Like, how much time is it? That time has a name. That's called capital T, time period. Hey, just like for the pendulum, capital T was time period. Be careful with capital T in physics. In a different context, it might represent tension, but in this context, represents time period. Okay. This is going to be in some number of seconds. Okay. That's the time to cycle one wavelength. Okay. So how much time does it take to cycle once? Well, that's called time period. Okay. There's also this property called frequency. And that's the reciprocal of time period. Okay. And that'd be measured in hertz, which is called Hz, right, is the symbol for that. Right? Hz is hertz. Right? And what is 1 hertz in terms of base SI units. Right? Well, I see frequency is 1 over time period. Isn't that like 1 over seconds? Right? That's what 1 hertz is. 1 hertz is 1 cycle per second. And you can call it like 1 over seconds. It's the same thing. Right? Is that right? Right. Okay, so we're sitting on the dock. We're watching these ocean waves come in. We know between Bob, like what that distance is. Maybe it's like 3 meters. Right? We brought a stopwatch, so we know let's say it takes like 1 second for that to happen. It's like Bob, right? It takes like 3 seconds. Hey, do you think there's some associated wave speed with that? So, right, the waves are coming in at some speed, right? And this is going to lead to the wave formula. Wave speed is equal to wavelength times frequency. Right there. Okay. We point this out on the AP equations. Right. Well, AP wrote it a little bit different. It gets its own box. Right. Here's AP's equations. They give its own little box right here, waves. They arranged it a little bit differently, but it's the same thing. Right. I remember, according to how AP's accounting for things, you guys should not actually see this equation pop up on the AP exam, but I want you guys to know it anyway. I went to, when I was at university, some of my engineering classmates had sort of kind of remembered this formula, but they couldn't remember exactly how to put it together. Like, well, there's like speed, there's a wavelength, there's a frequency. I can't remember what's multiplied by what. It's like, oh, well, if you got that far, just think about how units work, right? I mean, that's one of the things I want you guys to get out of a class like this. Right? So let's put this all together. Wavelength, that'd be in meters. Right? Frequency, that's in hertz, but that's hertz is the same thing as 1 over seconds, right? So you got meters times 1 over seconds. Oh, meters times 1 over seconds. Isn't that like meters per second? Which exactly describes a velocity. Yeah. You guys see that? Great. I've got some demos for you guys. This first one is auditory. You guys hear like 1 beat per second? Okay. What frequency is that? How many hertz? 1 hertz. Yeah, 1 beat per second. That's 1 cycle per second, 1 hertz. Okay. And how much time between each beat? 1 second. Okay, so that's pretty straightforward, right? Reciprocal of 1 is 1. How about this? Did you guys hear 2 beats per second? How many hertz is that? 2 hertz, 2 seconds per second. And how much time between each beat? Half a second, right? 1 over 2, right? Guys hear 4 beats per second? How many hertz? 4. How much time between each beat? 0.25, right? 1/4 of a second. Guys hear maybe 8 beats per second, right? How many hertz? 8. How much time between each beat?
0.125.
Yeah, 0.125, because right, 1 over 8, right? 1/8 of a second. Right? Okay, so you can see that reciprocal type relationship, right, between the frequency and the time period. What if you kept ramping that up? And that last one was 8 hertz, but what if I ramped it all the way up to like 440 hertz? Do you think at some point your brain would not be able to distinguish the beats more, but it just sound like a hum, like, right? There's actually a reason I picked that number 440. Why did I say 440 hertz? Who knows? Because that's defined as a what? Gonna say an A note, right? Gonna say like an A note, right? So one of the keys on the piano, if you hit it, it's one of the A keys. It'll give you 440 hertz. That's one of the definitions of an A. Okay, so this corresponds to like a musical tone, is what it would be. Right? If you get like enough beats, I'm like a hum. Okay. It's got that. Okay. Let me flip my screen over and share it for. See the class recording. Share screen. Share. Okay. Oh, too many windows open. This animation. So got this block bobbing up and down. Ooh, that looks like it has some kind of periodic motion, a lot like the pendulum, doesn't it? Actually, I pointed out the formula for you guys, and it's hanging from my ceiling right here. The formula for the time period of that bobbing back and forth looks a lot like time period of a pendulum. 2 pi times the square root of m over k, where m is the mass of that red block and k is the spring constant. How stiff is the spring? Okay, if you know the mass block and spring constant, you can calculate how much time it should take to bob back and forth. But something else to notice. Do you guys see that green dot on that blue circle going around? Okay, now that green dot has a constant speed, not constant velocity, so it changes direction, but constant speed. If that was like a great, oh, hey, where's my energy go? Now, if that was, get a new one. If that was like a green race car on a blue track, then the speedometer reading would be constant all the way around. Right. But you guys notice that those 2 green dots, the one on the block and the race car, both have the same vertical location at all times. I see that? Like if you were to like lay a meter stick over both of them, that meter stick would just stay level. It would bob up and down, wouldn't it? Right? So maybe if you started to ask, well, I wonder what the vertical position of each of those green dots is as a function of time, which of course they're the same because they match. How do you guys think that would be a sine curve? Sine curve. Yeah, and we just did those. We just did all the graphs on those. Okay. So they gotta have a vertical position. They also have a velocity, which just be the rate change of that, maybe like a cosine curve, and you can keep going on, like acceleration, blah, blah, blah. There are, into like wave propagation, there are 2 main physical types of waves, and you see them right there. So transverse versus longitudinal. The definitions of these, do you guys see how transverse each particle motion is just like up and down? Like if I tape a red flag to some part of the slinky, it just goes up and down. Okay? But the energy propagation is left to right. So whenever you have particle motion and wave propagation that are perpendicular to each other, that's what marks a transverse wave. Longitudinal, everything's in the same direction. So each particle motion is back and forth. The energy propagation is left to right. So if those are parallel to each other, that's what marks a longitudinal wave. Now you guys might know some of these kinds of waves. You guys are hearing me right now because there's a sound wave going from my voice to your ears. A sound wave is a type of pressure wave. What do you guys think a pressure wave is? Transverse or longitudinal? Longitudinal. Yep, sound waves are longitudinal. And sound waves need the medium to pass through. So if you could somehow like see the air molecules, they'd be like compressing, like getting like more pressure, less pressure, like a pressure wave. The next lab we do is actually going to involve, well, sound waves that are longitudinal. It's a lot easier to draw a transverse wave. So sometimes I'll draw a transverse wave, like representing a longitudinal wave. I'll tell you guys about that in the future. But what do you guys think light waves are? Do you guys think light waves are transverse or longitudinal? Transverse? You guys are right. And I will prove that to you guys. So, and also light waves do not need a medium to travel through. That's why light can get to us from the sun. It goes through like the vacuum of space. I put the screen over and prove to you guys that light waves actually are, hold on, gotta get this right. Am I sharing my screen? No, stop share. Okay. The light waves are transverse. So there's this concept of a polarizing filter. I do have, there's my polarizing filter. Oh, there it is. Okay. So imagine you have like a slinky. Okay, you guys see a straight slinky right here? Okay. Now you can create both of those kinds of waves with slinky. You can do longitudinal by like pulsing like this, right? And you can create a transverse by shaking it back and forth like this, create this like S-like shape, right? Like a transfer. You can do either one. Right? What if you have like this polarizing filter? So let's say I build this thing out of wood. So I got like these wood sides, I've got these wood slats. Okay, well, a polarizing filter, if you have a longitudinal wave goes through, it'll make it through no problem. It doesn't care about the filter. But if it's transverse, it'll only let the wave through in one direction. That's why it's polarizing. That's why you call like a polarizing filter, right? Only lets it through in one direction. See, if you shake the slinky back and forth, like right, left, it still gets through. But if you shake it up and down to create that kind of transverse wave, like up and down, see how the polarizing filter is going to like block it? You guys see that? Okay. Well, let's see if can light be polarized. I got some polarizing filters here. You guys ever buy sunglasses that are polarized? If you do, you can do the demonstration I'm about to do here with those. Also, your computer screen, the light coming off that is polarized. Right? So let's say this lets it through horizontal and then horizontal. Right? If I put those over each other, okay, well, horizontal, it gets through. Right? No problem. Right? But is ready for something weird? What if I take one of these and turn it 90 degrees? So it's like horizontal and vertical. Right? Let's see what that's gonna look like. Oh, look at that. No light gets through, right? As each direction. And then, yeah, like none gets through that way. Right? So there you go. There's evidence that light actually is polarized. Share screen to share. Right. Niche. Oh, let's look at interference patterns. Oh, whoops. I gotta flip the screen over. Right, interference patterns. So got a couple of wave pulses. You guys see how maybe that's like come on here, like 10 centimeters and 10 centimeters. Okay. What do you think is going to happen when they cross over each other? 10 and 10 makes like 20. Yeah. Do you guys see like Bob to like 20? 10 and 10 makes 20. Right? You guys see that? Okay. Okay. So that's called constructive interference. Do you think that there's such a thing as destructive interference? Destructive? I wonder what that would look like. So we got a positive pulse there, a negative pulse right there. Right? Now, what do you guys think is going to happen? I pause right here so you guys can think about it. Right? When those two pulses cross each other, do you think they're going to cancel out?
Yes.
Let's find out. Oh, yeah, they did cancel out. Oh, no, there was more of that story. Oh, they just went through each other. Oh, look at that. Right, let's do instant replay. It's got positive pulse, negative pulse. Okay. So they do cancel out when they're right on top of each other. But that's not all. They're actually traveling through each other and they just continue on their way. Oh, that's really cool, isn't it? There's one more detail that I want you guys to see that actually could be an AP question also, which is you guys see this pulse, this positive pulse that's moving on to the left. Okay. I want you guys to see what happens when it reflects off. I think somebody's like holding it like barely off screen here. When it reflects off this left point, okay. Watch what happens. You guys see how it like turned upside down? You guys see that? Let me go and show that again, just in case you missed it. So follow this positive pulse. Okay, there it is crossing, and then here it is emerging on the other side, and then bam! You see how it reflected upside down? Okay. It is possible you'll get that question: is what would happen to? Well, you guys see the answer if they ask that. Okay. Let's look at standing waves. Okay, so you're going to look at this is a transverse wave here, although you could also do this with longitudinal waves, but we'll do this for the next lab. Okay. Now, a standing wave, it looks like it's just kind of bobbing up and down in place. You'll get these nodes. See how there's a node right in the middle? If I walk up and grab it, slink right in the middle, then it doesn't really affect the motion of it. So you can grab it at the node, doesn't make a difference, right? Okay. Oh, now here's all different standing waves that you can create, right? All these different standing waves. Okay. Let's count some things here. How many? Let's say how many nodes do you see? See a node here, 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 and probably each of the hands also. There's kind of bobbing back and forth. So do you see 5 nodes? Right, 1, 2, 3, 4, 5 nodes. Okay. And there is also 2 troughs and 2 crests. So I could call those 4 antinodes. Right? If you had this, let's say this was like a string hooked to an oscillator. It was just going. AP likes to ask this question. I've seen oscillate before. Right? Then wouldn't this look like? They might refer to this as 4 loops, because it would look like there was a loop here, a loop here, a loop here, and a loop here. I got videos on that too. Might show you guys a different day. Okay, but how many wavelengths do you guys see? How many wavelengths? Let's say one way you can count wavelengths is crest to crest, but another way you can count it is full S shapes. You guys remember that? Okay. So going from this hand on the left to right here, the middle of the screen, isn't that like one full S shape? Is that? Okay, and I see 2 of those, so there must be 2 wavelengths. Guess that 2 wavelengths? Okay, so 4 loops corresponds to 2 wavelengths. That's 2 full wavelengths. Let me rewind the video a little bit. How many wavelengths do you guys see right there? 1 and half. You guys see 1 and a half? Okay. Let's rewind a little bit more. How many wavelengths right there? Exactly 1, right? That's 1 full S shape. You can copy paste that next to itself. And the first one you start off, you might call this like a fundamental type situation. How many wavelengths is that? A half. Yeah. Okay, so you can go, okay, so you guys see the pattern? You can go a half, 1, 1 and a half, 2, Right. And probably just continue from there, right? Increase by increments of half a wavelength each time. Right. Now that's true for this type of wave. Say if you have a string between two people and you want to set up a standing wave, you go a half, one and a half, two wavelengths, and so on. Right? Now, if you have a longitudinal wave, like a sound wave, the lab we're going to do next involves sending a sound wave down a PVC pipe and setting up some resonance, like a standing wave, but with sound. Now, the physics of pipes, I've got posters for them too, work a little bit differently than string. I think it goes like a quarter, 3/4, 5/4, something like that. But you guys see the strings right here. You guys see the pipes right there. And then there's also different physics. Actually, I just told you guys what it would be for a pipe closed at one end and open at the other. But the physics is different for if the pipe is open at both ends, like a flute or something like that. So you have different kinds of standing waves you can set up. Let's do. Okay, start to combine these ideas. Oh, and I remember what I was going to say on standing waves. This is how your microwave oven works. So a microwave, it's like some wavelength of like non-visible light. And it might have a wavelength of like somewhere about 12 centimeters, somewhere there. And the width of your microwave box is some exact multiple of that. So that when the microwave is sent across the box, it will set up a standing wave like this, and it will constructively interfere with itself. And that's how you can heat something up really fast. Okay? You guys ever notice there's like hot spots and cold spots, and whatever you put inside a microwave oven? Okay? Well, the hot spots would be like these antinodes, and the cold spots would be like these nodes. Right? Yeah, that's why there's a turntable inside your microwave oven, so that it mitigates that effect. Right? Otherwise, you get like a bunch of frozen spots. Okay. So let's combine these ideas now. You guys got constructive interference. I missed one more detail. I'm sorry. Let me go back to destructive interference. Did I tell you guys about noise canceling headphones? Okay, great. So this is back to destructive interference. I'm going back a step. This is how noise canceling headphones work. It's actually an active process inside the headphones. You have to turn them on, it's like battery operated, whole deal. And the headphones will take the outside ambient sound and interfere it with the they'll turn it upside down, like invert it, interfere that with the original ambient sound, and then what gets pumped into your ears is basically like that right there, and that will cancel the outside sound. Because that's how it works. Okay, so we got interference, we got standing waves. Okay. This is going to bring us to resonance.
My name's Chase, and I live in California, and I'm gonna try to break this wine glass by only my voice.
What is happening?
Mom, look. It'll never. Mom, I broke it! Look it! I did! I broke a glass! I broke a glass, people!
Try this yourself, but be careful because glass is a little bit dangerous. You can hit what's called a resonant frequency for some object, and I forget if it's the diameter or the circumference of this glass that matters. And well, the internet's not really working right now, but the sound wave that you send out has a wavelength that is that matches one of those properties. Again, so you can see the diameter or circumference. Then you can set up a standing wave, keep pumping in that wave, keeps pumping in energy. It'll create a constructive interference, and it will resonate until it actually breaks the object. This is something that engineers have to worry about when they're constructing buildings, because different buildings might have an associated resonant frequency. One story I remember, I went to University of Florida, and I was taking engineering classes. So one of the relevant stories was there was this center, everybody called the old O-Dome. It was, I think officially called the old Connell Center. And it was like a dome-shaped structure. And the engineers designed this thing and started to construct it. And some engineer went back and checked, well, what's the associated resonant frequency of this particular structure? and it ended up being 2 hertz. And then when he figured that out, everybody kind of freaked out. It was like, oh boy, we're gonna have like stadiums full of like basketball fans all standing there like, go Gators, or everybody in the bleachers, right? Oh yeah, that's about 2 hertz right there. So you might actually get like a case where you could like take down the whole structure. Now they went back and did some engineering solutions and reinforced it so that wouldn't be a problem. But that was one thing they had to look at. It's going to lead us into how many guys are in ROTC? ROTC. Right? One thing you learn is to march in step, left, right. Different reasons for that. One reason is you can show you can move people more efficiently if everybody's marching in step. But there's one place that you're told specifically to break step, like do not march in step in this one location, and that's over a what? Bridge. Yes, over bridge. Now, why would you not march in step over a bridge? Well, allow me to demonstrate. So, troops marching over bridges have collapsed bridges before because of this this resonant frequency phenomenon. Now, it's not exactly what's going on here, but it's really similar. This is a very famous case called Tacoma Narrows Bridge. Some of you guys might know about this. This is back in 1940. Tacoma Narrows is over in Washington State. I want to say it's nearby Seattle. They opened this bridge, and opening day, here it is. Now, the bridge did bob up and down a little bit, but engineers were keeping their eyes on that, saying, okay, well, it's not really causing any cracks. I mean, this whole thing is concrete and steel, right? So, okay, we'll keep an eye on it, but this was open to the public for a few weeks, but not very long, because one day it comes across this crosswind, and the bridge starts doing this. Yeah, this wasn't very good. It's concrete and steel, right? Now there's an engineer walking around out here. He ended up being okay. He got off the bridge before classes. You guys kind of see where this is going. But here's his car. He's trying to walk along the snow line. If you count the time period of this oscillation, I want to say it's pretty close to 5 seconds. I think is what it comes out to, about 5 seconds, which means the resonant frequency is about 0.2 hertz. And there was this crosswind blowing across this bridge that was just constantly pumping in energy. It set up this standing wave, and then well, eventually tears this bridge down, which you guys can see here in a moment. Well, just zoom to that. Now we don't really see bridges do this nowadays. Why? Well, because this was almost a century ago, and we use examples like this to build on our engineering knowledge. I'll let you guys think about this tonight, and then tomorrow pick up. I've got some more demos for you guys and continue on. But I want you guys to think like, why would this happen? What do you think possibly the design flaw was that would cause this to happen? That now after this thing collapses, what they actually did was just went back and they actually went back and rebuilt this bridge and just made one small design change, and the bridge functioned perfectly fine after they did this one thing. What could it be? And so yeah, you guys think about that overnight, and that's about as far as I've gotten in my classes today. So that's about what we'll pick up tomorrow.